Okay, so we're recording, um, and what I wanted to do first is I want to talk about what we have left to do, because we only have this week and then 2 weeks afterwards, and we're done. Summer goes so fast, but what we have left to do is I'm going to talk about labs in a minute, but this is the material that we have. And this stuff is so much easier than what we just did. But we really have 5 things to cover. We're going to cover angular momentum today, which is super easy. And I could have covered it before exam 2, but I figured I'll push it back. It's useful for gravity. And you'll see today that it's pretty easy to actually mathematically do. If you understand the one-dimensional collision stuff, angular momentum is super easy. And then tomorrow, I'm going to cover Kepler and universal gravity. And there's some cool stories about, so Kepler may have murdered somebody named Tycho Brahe, and we'll talk about that tomorrow. And then we'll talk about how to mathematically do planetary orbits, and that's super easy. You just have to figure out your variables, but it honestly is easy. The other side of that is what's called universal gravity, and we've been assuming gravity was 9.81 meters per second squared. We're going to figure out how Newton actually figured out what gravity is between any 2 objects anywhere in the universe. And when we do that, we have to redo our MGH, our potential energy of gravity. So there's a little bit of that there. And that's a little hard, but the rest of it's easy. Then next week, we'll talk about fluids. Fluids is super fun, super easy, and you already know it, which is you may not know that you know it, but you actually know fluids already. Buoyancy is just summing forces like we've done for the free body diagrams for a mass hanging on a rope. Pascal principle is easy. And then Bernoulli's equation is actually energy. You may have learned it before, but it's how to find the fluid and pressure at any, the flow and pressure at any point in like a pipe. And what it really is it's the energy equation that we have already. It's just turned into pressure, which makes it super fun and easy because we already know it. Then we're going to study pendulums, and pendulums only have 1 equation, but we're going to talk about how pendulums work. It's a really easy equation to memorize, and you just have to play with it a little bit to see what it can tell you. And finally, the last thing we're going to do is oscillations. And what oscillations are is, imagine a block attached to a spring, and it can move back and forth. Damping means friction, so it can move back and forth without friction or with friction. And it turns out that that's something called periodic motion or simple harmonic motion. When we do that, I'm going to show you how to do the differential equation. Some of you have had differentials, and that's fine. Those of you who haven't yet and may eventually take differentials, I want to show you how it's done so that you're not kind of scared of differentials. Differential can be scary because it's a lot like physics in that, unlike other math, in differential equations, you have to figure out what your equation is and then set it up, and then you have to try and solve it. And sometimes you have no idea how to solve them. So in differential equations, you're taught methods of solving different types of differential equations. And so I'm going to go through a little bit of that with you just to help you for down the road. The actual equations we'll use are, you find the amplitude, the phase angle, and the angular velocity, and that's it. You already have the equations. You just have to figure out what the variables that you need to plug in are and use them a little bit. So this stuff is much easier than what we did for the last 2 weeks. You're going to find probably that you like it more because it's stuff you know, like planets orbiting, or fluids like in your sink, how fast the fluid comes out of your sink. Pendulums you can do. That being said, that brings us to labs. I saw an email today that said something about you guys have to turn in your ILabs next week, which is ridiculous. If we do that, if I find that's out is that's true on Friday, as soon as I know for sure when, I will send an announcement to everyone, or I might even send a message through Canvas telling you when you can turn in your ILab. If we're unable to do that, I want to do a pendulum lab and a buoyancy lab, and I really wanted to do one other lab. I wanted to do 3 more labs. We'll at least do those, and we'll have to get the data. So if we have to turn them in next week, probably Tuesday, we'll go through and make sure that we get the data, and you can still work in groups of 3. So I'll have to have at least one of you from the group be with me on Zoom, and we'll go through and get the data for both the pendulum lab and the buoyancy lab that I want to do. If it's pushed back a little bit, we may do another lab. Those 2 labs are pretty easy to do the error analysis on. They're pretty easy to do. So hopefully that'll all work. Anyway, that's all beside the point. I just want you guys to know what we're doing. Our final is on 2 weeks from tomorrow, which is ridiculously fast. And that final week, I had planned to do 2 days of review and a lab, but we'll make sure that you guys are okay with the final. How the final actually works is it's basically a question from these 4 bottom topics. And then usually an energy question and a question on like free body diagram or projectile motion. You'll see that, you'll get practice finals. But I like to have a little bit of a, I forget what that's called, my brain's not working. I like it to cover everything we've done a little bit. So just to make comprehensive, I like it to be a little comprehensive. So you're gonna find that these problems are probably pretty simple, but the 2, if you kind of did bad on exam 1 or exam 2, those 2 comprehensive questions might be a little hard, and we'll go back over them. The only good thing is they're fresh. You remember them. So, okay. Anyway, that's stuff for later. I don't think this lecture will be long. I'm not planning for it to be very long. And there's a few videos I want to watch. So get comfortable. If you have questions, feel free to speak up. Please speak up. And if it's in the chat, I don't know if it'll pop on. So I'm going to actually share my whole desktop. I have to admit something to you guys. I actually recorded this last night, and when I went to the video screen, I showed a little video, and then when I went back to the PowerPoint, I forgot to move away from the video to share the PowerPoint screen. So I realized there was like 10 minutes of me talking to doing math, and the screen was on the video, and I decided, I'm not going to edit it. I'll just do it live with you guys. So that'll probably work out better so you can ask questions. Anyway, let's talk about angular momentum. So a few weeks ago or a week ago, when we talked about an object moving with velocity. So let's say we have some little point particle and it's got mass and it's moving with v. We said that it had this quantity of momentum called mv, and we called that p, and it was a vector. It could be in the x and the y and the z. And the collision equations and the rocket equation, all those equations came from the fact that if there was no force, so no force, because force is dp dt, if this was 0, what we got was that 0 was the change in momentum. And that meant that momentum was conserved, which meant that the whole system's momentum, this could have been m1 v1 initial plus m2 v2 initial, and that would be equal to m1 v1 final plus m2 v2 final. And that's how we did collisions. We did collisions with this idea of a conservation of linear momentum. And it turns out that there's another type of momentum that we can talk about. And this type of momentum is far more difficult to understand in a weird way. So And the reason why is normally when we talk about this momentum, we already know where our origin is, right? We assume that there's some origin that this B is relative to. And we don't think about it at all. We just think, oh, it's moving with some velocity. Something happens and the velocity changes, right? Or the mass changes, so the velocity changes, or whatever. Well, in angular momentum, we have to choose an axis that the particle is rotating relative to. And what I should really say is rotation isn't what you might think. Rotation is just movement relative to an axis. For us, we're going to imagine that this mass is moving in a circle, uniform velocity with omega, no alpha, let's say. And we know that it has this tangential velocity and it has a mass. So it would have a vector that would be P, the mv vector, which was mvt, but because it's at a radius vector from our axis of rotation, and remember your right-hand rule means that this comes out of the page and a z is positive by right-hand rule. If we do this quantity called angular momentum on this particle that happens to be moving, what we get is we get r cross p. And you do that just like a torque. We had to do this after torque because you have to understand how to do the cross product. If I cross r to p, what I see is I get they're 90 degrees off, and almost everything we do, they'll be 90 degrees off. They don't have to be. I mean, it could be at some weird angle, but we're going to assume in this equation, really this would be rp sine of the angle between them. We're assuming that angle is 90 degrees. So what we get is mvr. And that means that angular momentum has units of kilograms, meters per second times meters, which is weird. That's kilogram meters squared over seconds, or newtons over, or newton seconds. Angular momentum doesn't have units, just like regular momentum. Linear momentum doesn't have units. You just say that it's angular momentum, but the units are actually kilogram meters squared over seconds, which is kind of messy. I don't know why they never gave angular momentum or linear momentum units. This is really the secret to so much motion that you probably never ever thought about. Because angular momentum is conserved, if you go back to thinking about, remember the firework problem, where the firework blows up and one part of it loses all of its linear momentum and the other part gains all of it. Because momentum is conserved, the whole thing has to have the same total momentum, but if one part loses it, the other part gains it. Well, angular momentum of a system works the same way. It's always conserved unless there's some outside force. And if we take the whole universe to be our system, there's no outside force. Everything's an internal force, meaning angular momentum is conserved everywhere. And that if you change the angular momentum of one thing, it changes the angular momentum of another to conserve it. That's really important. And you may not understand what I'm saying yet. You will understand in a few slides exactly what I mean. For a system, you can add all the angular momentum of all the particles. So you could have a bunch of particles like a gas, and they're all going in their random directions from the center of mass of the gas. So you draw an R vector out to each of these masses and compute MV crossed with, well, R crossed with MV. And what you get is you get M1, V1, R1 plus M2, V2, R2 plus M3, V3, R3, etc. for all of them. You just add them together and you call that big L. Big L is a system's angular momentum. All the pieces, you have to define an angle or an axis. Normally on an object or a system, we define that axis to go through the center of mass. So imagine you had a wheel that's rotating, right? We know the center of mass is in the center. So we'd say this wheel had some L, which is actually a combination of all the little tiny pieces of mass that make up the wheel, each of their angular momentums. what this means right here, supposition just means that you can add them all together and assume that they don't affect each other. When I say characterized, all I mean is that you can have L in the X, L in the Y, and L in the Z, and that's a little hard to think about because technically this wheel could also be rotating like a coin on its edge spinning. And it could also have some maybe spin in this direction if it were floating in space. So it could have angular momentum around every axis. And then what you would say is L is Lx squared plus Ly squared, et cetera, right? But in general, we're only going to consider the body axis, the center of mass axis, and how the angular momentum changes about that axis. So we don't really need this, but later on, if you're an engineer or going to be in physics, even if you study chemistry and stuff, you may encounter this in different things, and we'll talk about that right now. So let's imagine that we have two particles, and this is the rotation Z positive. So I have particle 1, and I have particle 2, and they're at R, and they're at R. Sorry, I should do that backwards. So I'm going to say this is negative R and this is R. This is mass 1 and this is mass 2. And mass 1 is going down and mass 2 is going up at this particular time. What is the angular momentum of this system? Well, L would be the individual ones. Note this is negative. So I would get M1 minus V1 minus R1, I guess, plus M2 V2R. Or if they were the same mass and had the same velocity and the same R, I would get 2mvr. So I would just combine the two angular momentums of each one as they spun around and around and around. Okay. Opposed to that, what if they were going in opposite directions? So this one was going up, V1, and still at negative R. And this one's at R, and it's going up as well. And this is M2. My angular momentum would be M1 V1 times negative R plus M2 V2 R. And if these M's were the same and the V's were the same, my angular momentum would be 0. This guy is rotating around the axis in a clockwise direction, which means it has negative L, or little l, I guess. And this one's rotating counterclockwise, which means it has positive L, and together they have no angular momentum, okay? Finally, I could have one of them traveling around the z-axis, and let's say this one is spinning around this one that goes up to here. It's around the x-axis, right? And they can be doing that. And then, so if they were MVR, this would have L to the X MVR and L to the Z MVR. And what you would end up with is you would end up with L is MVR squared in the X plus MVR squared in the Y, or I mean in the Z. And so what you would end up with is 2 times MVR squared, which means you would end up with L would be root 2 times MVR, if M and B and R were all the same. Why is that important? Atoms and the electrons of atoms have angular momentum. And one way to define things in quantum mechanics, which you may study if you take 4C next, is you define them by their angular momentum. This also explains why atoms have to have certain angular momentum systems of atoms. And this is exactly what's going on based on how many electrons you have that are free. The ones that are locked in general, will have no angular momentum because they have enough to cancel each other out. It's weird. It's weird stuff that you'll see it there. But here's the cool thing. Planets have angular momentum as they rotate around the sun. So you can see these as atoms going, or electrons going around a nucleus. You could see them as planets rotating around a sun. You could see them as galaxies rotating around a galactic center of mass of a galactic group, you could see them as two people on ice holding hands and rotating around their center of mass. Everything has angular momentum, from the smallest thing to the largest. Now, the weird thing about it is where we choose our axis, kind of the angular momentum depends on where we put our axis. Remember when we talked about the train? And you're throwing a ball up and down on the train. And this ball isn't rotating, it's going up and down. So it doesn't have angular momentum, right? But I see that ball doing projectile motion, and about a point on the train, I see it as rotating around that point with projectile motion. So angular momentum does depend on, it's relative to where you choose your axis. In fact, you could have angular momentum that you're not thinking of. If I had an axis here and I have something moving in a straight line, so it has B here and it has B2 here, right? I have an R vector and I have an R vector to those 2 points, and it's changing its angular momentum between those points. Even though it's not what you would think of as rotation, it has angular momentum about that axis. So the key takeaway here is you have to define an axis. Most of the time, what we're actually talking about is the body axis of something like the nucleus of an atom and how the electrons move around that body. So you usually have a clearly defined axis, but you don't need to, which makes this all really weird stuff and hard to understand. As long as we stick to body axes, we're fine. Now, what is a body axis? So for a body axis, imagine a top, you know, a prism that's spinning about a point on the floor. So this would be the body axis. Again, a wheel would have an axis through the center of it. That's the body axis. It could have one through here and spin on its side, but we're talking about this body axis. So what you would need to do in order to find the angular momentum is you would have to take the integral to get all that R cross P stuff, right? We don't need to do that. We've already done that. And what we get is we get I omega. I omega is the sum of all the little L's, and an integral is just a sum expanded to some almost infinite point, right? So we're only going to concern ourselves with the moments of inertia for objects that we know already from chapter, what, 9 was that? Or 10, where we know the moment of inertia of something. So for a wheel, right, that's rotating with some omega, say 2 rad per second, and some, it has a mass of 1 and a radius of 1, let's say, just to make this easier. We know I of this wheel is mr squared over 2. So that's 1 times 1 squared over, that's 1/2. And I omega, which is its angular momentum, is 1/2 times 2, or 1 kilogram meter squared over second. Okay? So anything that's rotating, that's an extended object, if we know its moment of inertia, we can find the angular momentum of that object. As long as there's no torques on there that would change omega, because remember, a torque is I alpha, right? And we'll talk about this in a minute, but so a torque changes the acceleration, and the acceleration changes omega. So the acceleration changes the angular velocity. So as long as there's no torques, this is conserved for the object, and the object continues to rotate at whatever omega is. This is actually true for a point particle. Now we know that we got MVR. If you plug in, if you assume that this thing's moving with constant R, which of course it is because there's no torques or forces on it, then V is equal to R omega. And so I can plug in for V, R omega, and I'm multiplying by R still, and what I get is I get mr squared times omega. But mr squared is the moment of inertia of a point particle. So you can see for a point particle, little l is just I omega. So what you have here is you have two ways of defining L. L is either MBR for a point particle, which is I omega, or for a bigger particle, it's I omega, I of the object. And if there's more than one point particle, it's the sum of the little L's. And that's all you have to do. You just add them up. So at this point, we have to ask, well, that's all fun and a bunch of math, and why would we care? Well, let's look at this. So torque is I alpha. We should already know that. We did that when we did our torque diagrams. We set up I alpha. And we know that alpha is the rate of change with time of omega. It's how omega changes with time. Well, if I put I inside, because I can change as well, it turns out, you could have like a top fall over or something, okay? You can have I change, and we'll talk about how I can change, but if I can change, then this is the change in the angular momentum over time is really what a torque is. So we lied to you about torques. What torques really are is the change in the angular momentum of the system with time. If there are no torques, again, this gives you the change. If that's zero, we see that this is true. And what this really means, though, is that I1 omega 1 plus initial plus I2 omega 2 initial is equal to I1 omega 1 final plus I2 omega 2 final, and we'll talk about this. But just like we did with linear momentum, if these objects are doing something weird, like they're combining together, right? If they're having some kind of collision where they're sticking together, then I1 plus I2 would equal I1 plus I2 omega final, okay? So here the system's moment of inertia changed, and therefore omega changed. Just to make sure you're clear on that, if this is true, then if I goes from I initial to I final, and I final is greater than I initial, so if this is bigger, this has to be smaller for this to stay constant. Let's say this is equal to 1, right? If this gets bigger, I final has to get smaller so that they stay equal, so that they're conserved. That's important. What that means is if you can change the moment of inertia of an object like your body, you could make your moment of inertia smaller while spinning around like a figure skater does. If you can make your moment of inertia smaller, you'll speed up. If you can make it larger, you'll slow down. And we're going to see that right now with a couple of examples, okay? I don't know how many of you have ever seen a potter's wheel, but just imagine a wheel that's rotating, okay? It's rotating counterclockwise if you look down on it. And what a potter's wheel is, you put clay on it and you can make a vase or whatever out of it, a cup, a bowl. Because it spins around, it's going to have a moment of inertia around that of mr squared over 2, okay? And this particular wheel is spinning with omega. And here we say it's 3 rads per second. So we can find this as 4 times a half squared over 2. This is our I. This would be 1/4. So this is a half kilogram meter squared. The initial angular momentum would be I initial omega initial. This is actually I initial. So I'd multiply 1/2 times 3. And I'd get kilogram meter squared over seconds, okay? Or actually rad over seconds. Rads aren't units though, so we can see that this thing has 3/2 angular momentum before anything happens. And then let's say I drop a 1 meter clay blob and it sticks, and we're assuming, and it's going to be at R is 0.25, we're assuming it sticks and there's no weird forces happening. It just sticks without causing a torque to the angular momentum. What happens to the speed of the wheel if that happens? We know that I initial, omega initial is I final, omega final. Or omega final, the speed of the wheel after this happens is I initial, omega initial over I final, or the initial angular momentum. So what is I final? Well, we already know that. If we have a point mass that gets added to our system, we have I initial plus I of the point mass of the clay, which is, we already said 1/2 for the initial wheel plus mr squared for the clay blob. This clay blob, mr squared is 1 kilogram times 0.25 is a fourth squared. That would be 1/16. So I get a half plus a 16th, and that ends up being 8 times 8 is 9/16. So I get 9/16 kilogram meter squared for I final. Doing this real quick, I know this was 3/2 over 9/16. If I flip this up, I get 8/3 rad per second. And 8/3 is like 2.7. I don't know what it is. I'm not going to put it in my calculator right now, but I know it's like 2.6 or 2.7. Look at what happened. We dropped a piece of clay on a wheel that was already spinning at 3 rads per second, and the mass stuck. So we changed the moment of inertia of the wheel because we added some mass to it off the axis. That caused the wheel to slow down. That actually slowed it down, but its angular momentum was conserved for the whole system. The blob had no angular momentum before it gained some. Where did it gain the angular momentum? Because once it's on this thing, it's spinning around. Well, it took some away from the wheel, right? And that slowed the wheel down in a weird way. So what you're seeing when that happened is you're seeing this conservation of angular momentum where the moment of inertia of the system essentially changed. That's kind of weird and really useful in a couple of examples that I'm going to show you. One of the examples is actually going to be the quiz tomorrow. Not this one, the second one that I do. But one way to imagine this is you could have, let's say, a rod that's spinning around its axis, right? And let's say you have a little mass. This is one of the things you do for the angular momentum lab that's attached to a string so you can force it to go to the center. So initially this thing would have a moment of inertia of a rod, ml squared over 3, plus the moment of inertia of, let's say, a point particle at L to the half. So plus m of the particle times L to the half squared. That would be your moment of inertia. You pull this block and it's at the center, and I final would just be, I'm sorry, this is over 12. I don't know why I'm always forgetting. I always want to put the, so afterwards it's over 12 plus m times 0. It's at the axis. So essentially you decrease the moment of inertia by sliding this thing in as this thing spins around. And what happens is I initial, omega initial is I final, omega final, omega final. And we see that omega final is I initial over I final times omega initial. This ratio is going to be greater than 1, okay? And therefore, is it going to be greater than 1? Yeah. Yeah, I'm being dumb. Sorry, that's totally true. So this, if I over I final is greater than 1, that means that omega final is greater than omega initial. What happened was, as this mass slid to the center, the moment of inertia decreased and omega sped up. For the system, you can see why that would be true. If the moment of inertia changes of the system, then it speeds up. Now your car, you may not realize, or maybe you do, some bicycle can do this. Cars do this inside transmissions, but imagine another thing. And so we did a bunch of pulleys that where we had 2 pulleys that came together and they spun at the same rate, okay? We're gonna imagine that we have a single pulley spinning and that we're going to then drop or somehow place against it a second pulley. So the initial would be mr squared over 2, and we'll say that m1 and m2 are both 2 kilograms, but radius 1 is 1 meter and radius 2 is half a meter. And initially this thing's going to be spinning with, say, 40 rad per second, okay? And then I'm going to drop that on there. I'm going to push it up against it so that they become welded together. And initially this plate isn't moving until it gets stuck, and then they're both moving together. So the initial would be M1, 2 kilograms over 2 is 0, is 1, and 1 meter. So initially this thing has a moment of inertia of 1 kilogram meter squared. It has an angular momentum of I initial times omega of 40 kilogram meters squared over seconds times rad. Now, once we stick them together, our I final is both of them. Mr squared over 2 for 1, plus M2 R2 squared over 2. This one is 2 over 2, which is 1, times a half. This is a fourth. So I get 1 plus a fourth, or 5/4 kilograms M squared. And now what I see, if I want omega final, when they come together, I get L initial over I final, which is 40 over 5/4, or 32 rad per second. Think about what that did. By having one gear spinning, like in the transmission of your car, which makes your car wheels turn, if you can suddenly add another plate to it that has greater mass, you decrease or you increase the moment of inertia of the wheel that's spinning, and you decrease the speed of the wheel really easily, really quickly. It's kind of a, this problem is, I believe, in your book. If it's not in your book, you can look it up. But they call it a one-dimensional rotational inelastic collision. I call it a clutch plate, because that's what happens with a clutch plate. You drop a new plate on and it slows your transmission down if you need to decelerate the car. And if you lifted it off, you would increase the spin of the wheel. So you can change the moment of inertia of a spinning pulley by adding mass to it or taking mass away. This works for humans though too. And before I show this, I'm going to show you a video right now, and I'm going to go to my desktop to share this because I want to make sure you can see it and that I don't. So hopefully you can hear this too. If you go into the hyperlink and open it. So this is a figure skater. And what we're going to see for this figure skater is we're going to look at her moment of inertia and her omega. So how she spins around her body axis. Her body axis goes straight down the middle of her body, points upward, and the rotation is around that. So if we consider straight up and the y positive as the positive rotation vector, we're going to see what happens. This video has no sound. I'm going to stop it for a second. So you can see her head is off this line where her axis of her body is. Her head's some distance away, her foot's really far away. You would figure out what the moment of inertia was by figuring out how much of her mass is off the axis this way and this way. And the greater it is, the further or the more mass you have away from the axis, the greater your moment of inertia. When she tucks up into a ball, she decreases her moment of inertia by getting all of her mass really close to the axis. And what happens when she does that? She speeds up. To come out of that speeding up, she throws her arms out or her leg out, and it slows her down. So I want you to look at how her body is positioned as she speeds up and slows down. Tucks in, speeds up. Throws out her hands, slows down. Tucks back in, speeds back up. This is all angular momentum. feet are out really wide, her head's out wide so that they're further away from her body axis, she's going kind of slow. Tucks in, speeds up as I decreases. The reason why we're using a figure skater is it's assumed that there's no friction on the ground as she spins. When she slows herself to a stop, she's actually causing friction on the ground, you'll see, so that she can stop her spin. But we're ignoring that on the ice so that we can assume that there's no torques at all on her body. Anyway, cool stuff. You can watch the rest of this video. This video just keeps showing more and more of it. You can watch it. It'll be on the PowerPoint that's already up. I just really wanted you guys to have a feel for what is going on here. So I'm going to go back into my PowerPoint. As I said, you already know this, though, what we're talking about. Think about this. So if you're like off balance, you're feeling a little dizzy, what do? You throw your hands out, right? You throw your hands out wide. If you've ever seen the guys that walk across like buildings in Las Vegas on a tightrope, they have a really big pole. The reason why they're using a really long pole is they're increasing the moment of inertia of their body on that line. And so if they start to rotate on that line, their moment of inertia is so big that the rotation is very slow, and it keeps them from falling off the rope. It makes it so that they can react to slight perturbations to the right or left much easier and keep themselves balanced. When you're feeling dizzy, you'll put your hands out to steady yourself. If you've ever tried walking on a rope above something, you put your hands out. The reason why you know to put your hands out is you don't know it, but subconsciously, you know that you're increasing your moment of inertia. And that's what's making you steadier, is you're basically more resistant to rotation. It's kind of cool. Let's actually look at the math of this. So assume that she's spinning around her body axis, and she has her fists tucked up close to her. What you would say is that her I initial is the I of her body plus 2 times the I of her fists. Okay, and we're going to treat her fists when they're up close as point particles that have a mass of 3 and a radius of 8. And we're just given what her body axis is. So this is 7 plus 2 times 3 times 0.08 squared. Okay, and if I do that, I have my calculator here. 2 times 3 times 0.08 times 0.08 is 0.034. So this is 7 plus 0.0384 kilogram meters squared. When she's in this position, as she's swinging around with some omega, her moment of inertia is 7.0384 kilogram meters squared. And we're saying that she's initially spinning at 12 rad per second. Now, she's going to throw her fist out as far away from her body as she can get them. And she's going to increase their radius to 1.1. But remember that this L initial was 7.0384 times 12 is 84.5-ish, 0.5 kilogram meters squared seconds rads. 84.5 angular momentum. Now, when she throws her fists out, what is I final? Well, I final is still her body plus 2 times I of her fists at the new 1.1 meters. So this is 7 plus 2 times the mass times 1.1 squared. And this ends up being 2 times 3 times 1.1 times 1.1, 7.26. So 7 plus 7.26, which means that her I final is 14.26 kilogram meters squared. By throwing her fists out, she's doubled her moment of inertia. And if we want to find her final speed, we already know that's L initial over I final or 84.5 over 14.26, 0.5 divided by 14.26 is 5.92 rad per second, 5.93 rad per second. So she slowed down from 12 rads per second to 6 rads per second. She basically went from doing, what would that be? 4 full rotations a second to only doing 2. Okay, not bad. She doubled her moment of inertia. She decreased her omega by half. That's pretty easy to understand, I think. Had she gone the other way, had she tucked her fist in, so her I initial would have been 14.26, and her omega initial would have been 5.93, and her I final would have been 7.0384. And you can see that her omega final would have been L initial over, this new over I final, which would have been 14.26 times 5.93 divided by 7, which is 12 rads per second. So if she went the other way, she would have sped up. That's obvious, right? If you ever watch figure skating, you should really see how they're making themselves rotate. It's actually pretty cool. Once you know this, you can see what they're doing and how they're making themselves speed up and slow down, and it's kind of amazing. We saw that skating video in the test. What he did was he actually applied a force to make himself rotate, and that I'm not going to get into. There's ways to do that using friction and gravity and whatnot. But yeah, if you start watching a lot of athletic stuff, it all boils down to angular momentum, how things rotate. And changing angular momentum, what's really, really weird about angular momentum is that, this is a bad way to say it, but nature doesn't want angular momentum to change. It's hard to change angular momentum. And you're going to see in this video right here, this is a video of a professor doing a wheel. And if you had a bicycle wheel like the one that he has, when he spins it, once it's spinning, you can actually feel in your hand when you try to move it side to side, it fights you. You feel a weird wobble where you have to create a torque. You have to fight it to make it turn. That you need to experience. You need to actually like hold it in your hands. And I really wish we were in the classroom because I could let you guys feel this. But what I'm going to do is I'm going to show you and I'll talk about it. And hopefully it'll make sense to you. So this video does have sound.
So in this demo, I'm on a nice little chair that rotates, pretty low friction. I also have a nice bicycle tire that's got some handles on it. What I'm going to do is I'm going to have an assisted divine spin this thing, and as this thing spins, it's going to have some angular momentum. And the question is, if I turn this thing, if it's spinning in one direction and I flip it to one side, I'm changing the angular momentum. Because of conservation of momentum, I have to compensate for that by adding my angular momentum. I might start spinning to cause myself to maintain this total angular momentum or conserved angular momentum. So I'm going to lift my feet off the ground, try not spinning. The assistant's going to come and spin this for me. I have some angular momentum. Now when I rotate it.
Now he had to actually fight that thing to rotate it. You can't tell, but if you look, his muscles are actually tense. You can feel it. It's weird. It's like this weird invisible hand that's trying to stop you from turning it. But when he does this, he's changing the angular momentum vector from pointing horizontal to pointing vertical. When he changes that, that causes a torque on him that causes him to rotate. And that's what you're supposed to see here, is by simply flipping this from horizontal to vertical, it causes his chair to rotate because he's on a frictionless chair. Angular momentum has to be conserved.
If I want to stop
flips
myself
it the other way, it will actually
I go the other way,
send him back the other way based on how the angular
spin back
momentum
around.
vector turns. It's weird, weird stuff with weird consequences to how motion works. This stuff, you can see why this particular thing wasn't on the exam. This stuff is really confusing. And now I'm going to talk about the most confusing of all, the so-called gyroscope. This particular video, I'm going to stop it after they introduce the gyroscope, and we're going to talk about how the gyroscope works. I'm going to say it now, and I'm going to say it again. Gyroscopes are in everything. They're in satellites. They're in your phone. They are in airplanes, drones. Everything that can possibly have a gyroscope has one. How they work is pretty amazing, but it's a bit of math, and it's a bit of difficult math. So I'm going to let the video get to a certain point, and then I'm going to stop it, and we're going to go through the math. But hopefully this will interest you, and you'll find it kind of strange. My question to you would be, is this anti-gravity? If I told you I made an anti-gravity device and I show you this, would you think that I was actually making anti-gravity? That is some 1980s graphics. So this wheel can spin freely inside this cage. Only that rod in the center spins. A gyroscope is a spinning disc anchored in a immovable cage so that you can rotate it. If this thing's spinning, take your right hand, there is a positive rotation vector that goes up because this thing's spinning counterclockwise, looking down on it, right?
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops.
That is super important. So the wheel is not spinning and gravity makes it just fall over on its own. It doesn't do anything special, it just falls over if there's gravity, right? It actually torques due to gravity, it rotates downward, but it doesn't do anything super special or neat as long as the wheel is not spinning.
Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel. The first thing I notice about the spinning gyroscope is that it resists attempts to change its position.
You can
A
actually
resistive force appears when I attempt to tilt or rotate the gyro.
You have to apply a torque to rotate.
Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright.
It doesn't want that horizontal.
When the wheel
rotation
stops, the
vector.
force disappears and the gyroscope falls.
So that's interesting. As the wheel slows down, it falls over.
Incredibly, this force will support the gyroscope like this. It appears to be levitating.
Black magic.
A spinning gyroscope will balance on a string.
Here's one of the
You can even lift the gyroscope with a string looped around one end.
He's just lifting it up, and the angular momentum, the rotation vector, is trying to stay aligned at the same angle to that spring. There's a little bit of friction, which it causes.
This interesting behavior is difficult to explain. Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has. To change the direction of the stone requires a force. Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation. The fact that gyroscopes will maintain.
So we're going to come back to this in a second. But I want to talk about the math of a gyroscope. And before I talk about that, we're going to have to visualize some things from overhead versus at eye level and blah, blah, blah. So I'm just going to imagine that it's on the pivot point. It has some lever arm, and then the wheel is at the end of this lever. Okay. And before I think of anything, I'm going to look at the forces on here. Now, there's obviously a normal force and there's a force of gravity. So this thing's trying to torque. But if I look at from this axis of rotation, if I look at the forces, I have the force of gravity mg and I have r, whatever this thing is, to the wheel that'll spin. That's a torque. If I look at r and mg and I turn r to mg, which way does this torque vector point? It points into the page. So if I'm looking overhead at this thing, this is the pivot point, and this is the wheel, right? There's down into the page is mg, this is r, and I get a torque this way, which is r times mg, or mgr. That torque, though, is actually going to cause remember that the torque is going to change the angular momentum of this thing. So this is equal to dl dt. If this thing had an angular momentum vector, it would cause it to rotate around, okay? That rotation around is actually called precession. So we have two things to talk about: how the wheel spins with omega and the precession around, which we're going to call this angle is phi, so we're going to call this big omega, the horseshoe looking omega. The last thing I need to comment on is if I have an angular momentum vector L, and then I have at some later precession time, after my angles change by d phi, I have L plus dl. This is dl. And from, assuming these are small enough, from the S is equal to R theta, we know that dl is equal to L d phi, okay? Keep that in mind. Or d phi is dl over L. If I divide this by time, okay, and I'm going to do that actually on a different slide. So I have from here, d phi is dl over L. Remember that this is the precession angle, or how the whole thing spins around that pivot point. Okay, if I divide this by time on both sides, what I get is that omega, which is d phi dt, this is like this with theta, this is our precession angular velocity, is the change of d phi with dt. That is equal to dl over dt over L. But we said this was our torque, that was mgr. So this is mgr, and this is I omega, right? But I for a wheel is mr squared over 2. This is omega of the wheel spin. So if I plug that in, I can see that I'll get 2, the precession is 2g over r omega. This is how that thing's going to rotate around the whole pivot point, assuming a couple things. omega has to be, this omega, this little of the wheel, has to be fairly fast in order for it to be stable. What actually happens is you get some weird effects happening, but as long as omega is fast enough, this thing will stay stable. The other thing I want to note is if omega is small, phi, or not phi, big omega is very large. So as omega slows down, this thing goes around faster and faster and faster. If omega is large, if that wheel is spinning really fast, it precesses very slow. And the last thing I want to talk about is this G. Now this G isn't 9.81, it's whatever gravity happens to be. And as I've gotten older, I'm convinced that really smart people are clever. They're not necessarily intelligent, okay? And there's a cleverness to using a gyroscope in that you could find G if you measure R times omega times the precession angular velocity divided by 2, you can figure out what G is. Secondly, since the wheel's spinning, it's always going to have some axis that G is perpendicular to its body axis. What that means is if you can put this thing in a cage that doesn't move and spin it around, you could put a sensor there, and anytime the cage moves, since as long as there's no friction, the gyroscope's not going to stop turning the way it's turning oriented to G, you can put sensors on the outside of this cage, and as the thing turns, you would know how you were oriented to the ground or to wherever G happens to be. We're going to see that in the video right now, that what happens is a gyroscope stays oriented how you spin it as long as there's no torques. And if there's no friction, it will spin forever. If you can measure the precession rate and the wheel spin rate, and you know how far the wheel is from the radius for whatever reason, this is one type of gyroscope. There would be other equations for other types. But if you could measure these values, you could find what G is, right? So you would know if you were over a planet with a different gravity, or you would know what height you were at for a satellite. Additionally, if you put sensors around it, as the satellite turns at different angles, it would always know which way down was. So it could compensate and keep itself level, like in a autopilot for a plane, or in a satellite, or in your phone. Your phone knows when you tilt it and it goes from horizontal to vertical or vertical to horizontal. How your phone knows that is it has little gyroscopes in it, little really small ones, and they know which direction is down. So they know that your phone is not pointed down anymore, that you changed its angle and it flips the picture for you. There's also something called accelerometers that help too, but gyroscopes do part of that job. We're going to see that right now with this plane, that hopefully this will illustrate it better than I have.
Maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position. If the aircraft rolls, electric sensors and contacts connected to the gyro send information to the pilot about the aircraft's orientation.
This video was made before phones. Otherwise, I think they would show you phones.
The Mars rover explores the surface of Mars using spinning gyroscopes to provide stability and navigational information. This full-sized robotic helicopter flies without an onboard pilot. Gyroscopes provide stability and navigation. Gyroscopes have become essential components of aircraft, ships, robots, and spacecraft. If you're interested in experimenting with a gyroscope, they are available from online science
So I tried to find one from Barnes and Noble, supposedly had them, but they didn't have them, which was really annoying. You can get one for yourself for pretty cheap and play with it. The main takeaway here is that along the rotation vector, it has angular momentum. And nature does not want that angular momentum to change, meaning you have to apply a torque to get it to change. And here, what's actually happening is it's maintaining its orientation of angular momentum, but there's a torque due to gravity down and at a distance r that's bringing that angular momentum vector around, causing it to precess or rotate around the pivot point.
And hobby retailers.
That's what you're
The
seeing.
gyroscopes
So it's moving the L vector around, rotating it around an axis here. So it has a precession big omega around. The wheel has a little omega with, right now, it's pointing right at us, and its angular momentum I omega is pointing right at us. And that
I'm
causes
using are
precess.
manufactured by Tedco.
So the point is this anti-gravity? And I guess I would put that to you. Would you say this is anti-gravity if I tried to tell you that I made an anti-gravity device? Or would you tell me, no, I'm full of it? The thing is actually using gravity. It's just using gravity to make something rotate opposite or perpendicular to gravity. That's super weird. That's just plain odd. Odd behavior. As I said, the cleverness comes from the fact that you can use a gyroscope, just a little spinning wheel, to tell you what gravity is if you know how fast it's rotating, which isn't hard to figure out. You can use it to guide a phone or an autopilot or tell you if something's level, all because angular momentum is always conserved. And as long as there's nothing outside force or torque, it won't change. And that's pretty cool. Cool stuff. So as I said, the faster the wheel spins, the slower it goes around. The slower it spins, the faster it goes around. I don't know how to make sense of that in your head. But anyway, so we're going to have a homework tomorrow after we do gravity. It'll have a little bit like the figure skater type stuff where you just have to figure out I initial and omega initial and I final omega initial. Tomorrow's quiz will be on like two gears or two wheels that come together. So you'll just have to basically do this right here. So just make sure you know how to do that, a one-dimensional rotational inelastic collision. Tomorrow, we're going to talk about Kepler and Tycho Brahe, and I'm going to put up a little thing from Harvard, a little 5-page history of the two of them. They were astronomers, and Kepler might have murdered Brahe. So I'm going to leave that there. Hope you guys are all well. I'm going to stop the recording and then we can talk for a minute.